So I'm going to move these to the denominator. And that 2 is really a hidden root. So really what I've got is I've got 1 over the square root of x minus 3 cubed times 1 over the square root of x plus 7 cubed dx. Now for us to get going with our trig subs, we need like x squared plus or minus something, right? So we got to get these quantities together, and the question is, can we do that? And the answer is yes. So properties of exponents tell us that if we've got a cubed times b cubed, that's the same as a times b cubed. And properties of radicals, which are once again just fractional exponents, tells us the square root of a times the square root of b is the square root of ab. So if we put all of that together, we can get to that. And now if we FOIL out the inside, we got ourselves an x squared plus 7x minus 3x, so plus 4x minus 21. There it is. So once again, we're using algebra here to take something we don't know how to handle into something that looks more like what we've been working on. Are there any questions on the exponent or radical properties here? So let's take a look at what's going on. I'm double checking I got the right. Yeah, x minus 3x plus 7. Okay. So x squared plus 4x minus 21. And that's all cubed. So what do I need to do with the x squared plus 4x plus 21 or minus 21? What do I need to do to get started? I don't have a complete square, so I have to complete the square. The first step, well, we don't have to worry about factoring out the coefficient of x squared because it's already a 1. So I just want to group x squared plus 4x plus something. And so to get this to be a perfect square, I cut this in half. Positive 4, cut that in half. That's a plus 2 for a quantity squared. And then I'm going to square that to get a 4. But in order to get this perfect square, I have to have a 4 that I'm adding. So I'm stealing a 4 from this 21. You can think of it that way. Or I'm adding in a 4. So then I have to subtract a 4 to keep the balance. So I get that. And so now I've got this integral. Any questions on completing the square? So I've got a variable squared minus a constant squared. I can make that a little more precise. I can let u be what? So we'll just do the x plus 2. Du is dx. And that'll get us to a variable squared minus a constant squared. Okay. If you let u be this thing squared, then your du would have a 2 times that to the first power, which is nowhere to be found. So we'll just let u be what's in parentheses there. And now we've cleaned it up to this. And so looking back, I've got a variable squared minus a constant squared, which means this is time for what substitution? Tangent substitution, you would want the sum of squares. Let's go back here. Because with the tangent, it's tangent squared plus 1 is secant squared. That's how you get the secant squared there. So we want secant. It's secant squared minus 1 is tangent squared. So yeah, so we'll let u be, in this case, 5 secant of theta. So the du would be 5 secant of theta, tangent of theta, d theta. Now the thing about the secant substitution is you're pulling from quadrants 1 and 2. And u squared minus 25 is 5 secant of theta squared minus 25. That's 25 secant squared of theta minus 25, which is 25 tangent squared of theta. Okay, so Matthew, this is getting back to the question you asked a while ago. Because in quadrant 1, the tangent of theta is positive, so the absolute value of tangent of theta is just the tangent of theta. But in quadrant 2, the tangent of theta is negative, so the absolute value of tangent of theta is the opposite of tangent of theta. So what we're going to have to do at this point is work through a quadrant 1 solution and see what the answer is, and then go back to see if we're in quadrant 2, what the difference is, if any. All right? So do you see why we have to break it into cases here, folks? On yesterday's secant sub, we knew what quadrant we were in. Here we don't. So let's just do the case. Our first case here is quadrant 1. So case here, theta in quadrant 1. So the tangent of theta is positive. So in quadrant 1, the integral 1 over it's the square root of 25 tangent squared, or excuse me, 25, yeah, tangent squared theta cubed times 5 secant of theta tangent of theta d theta. And so this is the integral of 1 over 5 tangent of theta cubed times 5 secant of theta tangent of theta d theta. And here we're using the fact that the absolute value of tangent of theta is tangent of theta. So now I have to cube everything and see what the heck I've got left over. So 5 cubed is 125. I can bring that out as a fraction. I've got 5 coming out in the numerator. I've got secant of theta tangent of theta divided by tangent squared theta d theta. And so I get 1 over 25 integral. Oop, it's tangent cubed, not tangent squared. I got ahead of myself there. Secant of theta over tangent of theta squared d theta. Okay, so far so good. So let's keep going. So now we got this trig integral to do. So I got 1 over 25 integral secant of theta over tangent squared theta d theta. We want to simplify this to see what we can get out of it. So let's do a little bit of trigonometry. So you can't keep back a secant tangent. You can't keep back a secant squared. If you turn the tangent squareds into secant squares, you'd have stuff locked in the denominator. So thinking back to trigonometry, when you had a complicated expression, you could always turn it back into sines and cosines. So let's do that here and see if anything presents itself. So let's start in the numerator. Secant is what in terms of sine and cosine? It's 1 over cosine. Good. So 1 over cosine theta. And tangent is what over what in terms of sine and cosine? Sine over cosine. Good. And that's being squared. So I would have 1 over cosine times the reciprocal of this. So the reciprocal of this, we'd have the cosine squared theta divided by the sine squared theta. Right? So when you divide by a fraction, you flip it. A divided by B over C is A divided by B over C is A times C over B, multiplied by the reciprocal. So this cancels out. And so with my integral, I'm left with 1 over 25 integral cosine theta over sine squared theta d theta. Let's make sure we're good with the fraction gymnastics there. And so now we're at the finish line because we can integrate this using a u sub from Calc 1. Now, the problem is we have already used u. So what I like to do is if we need to do another u substitution, I'll do a w. We can keep a cosine back and everything else is in terms of sine. So I'll let w be the sine of theta. So dw is cosine of theta d theta. So we're in the thick of it now, folks. We started with x's, we went to u's, we went to thetas, and now we're in w's. All right? This is why this is the last problem we do in this. So this is equal to 1/25th integral. This here is your du, or dw rather. We've got 1 over w squared. And this we can get using your power rule. Any questions on the substitution here or then the subsequent integration using the power rule? So now we got to work all of this backwards. Okay. All right, so once again, that negative exponent really means the w is in the what? The denominator. Okay? So it's an indefinite integral, so we got to take it all the way back to x's. So first step is we're going to go back. W was the sine of theta. So we'll take it back into the green. Minus 1 over 25 sine of theta plus c. And then we got to take it back to u's. U was 5 times the secant of theta. So that means that the secant of theta was u over 5. Now remember, we're in the quadrant 1 case. We're in the quadrant 1 case. So here's my angle theta. The secant is u over 5. So that's the hypotenuse over the adjacent. And since we're kind of getting close on time, you can use the Pythagorean Pythagorean theorem to get to this side is square root of u squared minus 25. And so the sine of theta would be opposite over hypotenuse and so 1 over the sine of theta would be u over the square root of u squared minus 25. We okay with the little triangle there? Quadrant 1? Secant's hypotenuse over adjacent. Get the missing side. Sine is opposite over hypotenuse. 1 over sine then, that's your cosecant, that's hypotenuse over the opposite. We get down to here. And so the last step is to plug the x's back in. So for the quadrant 1 case, the integral of x plus 3 to the minus 3 halves, x minus 7 to the minus 3 halves, dx, which is our very original equation here, is equal to u over 25 square root u squared minus 25. So we go back to what the u was, x plus 2. So we've got minus the quantity x plus 2 divided by 25 square root the quantity x plus 2 squared. Minus 25 plus c. And if you wanted to simplify this, you could FOIL this out to get your x squared plus your 4x minus the 21.
What if we're in quadrant 2? So how would things change if we were in quadrant 2? Oh, my pen tablet's not working. Here we go. So let's look at what happens if we're in quadrant 2. What changes? Well, in quadrant 2, so let's sketch this out. In quadrant 2, the tangent of theta is a negative number. So the absolute value of the tangent of theta would be positive. So that's the opposite of the original tangent of theta. So that means when we were going through and we had this show up, we had the square root of 25 tangent squared theta cubed times 5 secant of theta tangent of theta d theta. This would simplify to the integral of, well, we've still got the 5 secant of theta tangent of theta in the numerator. That's not going to change, d theta. But down here in the denominator, the square root of 25 is 5. The square root of tangent squared, that's our absolute value tangent theta. And this is going to be cubed. So what happens is we've got a negative tangent theta in there. So I've got my 5 secant of theta tangent of theta d theta over the 125, but I've got a minus tangent of theta cubed. And since it's cubed, that negative is going to stick around. All right? So you'd have a negative tangent cubed theta downstairs, which I could migrate out front. So I'd have a minus 1 over 25 integral of secant over tangent squared. And then I would do all the same kinds of things we did before, but our final answer then, instead of having a negative because of the power rule involved, we would end up getting this expression, 1 over 25 sine of theta plus c. So notice that negative then, right, we end up with a positive expression, which looks like, okay, well, is that going to give us a different answer? So we go back to our definition here. We have that we're in quadrant 2 now. So let's draw the triangle over here in quadrant 2. We have that u is 5 secant of theta. So the secant of theta is u over 5. But since we're in quadrant 2, remember secant is always the radius over the x value. Since we're in quadrant 2, the x value isn't a positive 5, rather it's a negative 5. All right? So our x-coordinate here is a negative 5. So that means that when we express the secant of theta as a negative 5, it's really a negative u, which makes sense because the radius has to be a positive number all the time. Radius is defined to be positive. If we're in quadrant 2, secant is negative, so the u itself would be negative, so the opposite of u would be positive. So either you can think of putting the minus u here to make sure the radius is always positive, or we know the secant is this ratio, and for this ratio to work, we've got negative and negative. Okay. So no matter how you slice it, when you go to calculate the sine of theta at this point, we can still do Pythagorean magic here and get the square root of u squared minus 25, because when you square these negatives, they turn positive. So that would mean that the sine of theta would be the square root of u squared minus 25 over minus u. So look what happens when you flip that over. So we get a minus u over 25 square root u squared minus 25 plus c. So then that negative comes back. Which is going to give us the same expression we had before in the quadrant 1 case. Okay. Now, in this case, like I said, the negative kind of went away and then came back at the end, so we get the same formula for both quadrants. Doesn't always happen like that. Case in point, if you look at the formula for the integral of the basic, let's say this particular one, using quadrants 1 and 2, you may recall that you do pick up an absolute value here. So if you took the time to go through the secant substitution on just this basic inverse secant integral, you would see that the negative doesn't come out in the wash, which is why the absolute values are in there. Okay. So this example had all of it in there, a bunch of review of everything. So I appreciate you watching here through to the end.